Sorry, just one second. Okay, and now I'll minimize this. Okay, cool. So I want to tell you today about the real Johnson-Wilson theories and some computations that I've made with them in joint work with Neetu Kitchlew and Steve Wilson. Okay, so let me just start by telling you what they are and why we're interested in them. So let me start with the Johnson-Wilson theories. So we're working at the prime 2, and these are complex-oriented cohomology theories with the coefficients given here, so the usual VIs with Vn inverted. And we know a whole lot about them. So from a computational point of view, we know the En cohomology of things like, well, projective spaces. We sort of get that for free. Eilenberg-MacLane spaces, so that comes out of some kind of more, so that comes out of hard work, some hardcore computations of Doug Ravenel, Steve Wilson, and Yagita, whose first name I don't know. And classifying spaces of various compact Lie groups or Lie groups and spaces in the omega spectrum for En. So I'll use this notation later in the talk as well. En sub k denotes the kth space in the omega spectrum. And so the En cohomology of this space, this constitutes unstable En operations. Okay, so these act on the En cohomology of spaces. I'll come back to this a little bit later. And a whole lot more. So, you know, among all cohomology theories, we know a whole lot about the Johnson-Wilson theories. Okay, now I want to tell you a little bit about the real Johnson-Wilson theories, and to do that, I need a little bit of equivariant notation. So by a genuine C2 equivariant spectrum, I'll denote those always with boldface. So boldface E is a genuine C2 equivariant spectrum. And it's just a collection of spaces. Here I mean the spaces in the omega spectrum, indexed over representations of C2. So here this means the representation that is A copies of the trivial representation plus B copies of the sign representation. So our spaces in the spectrum are indexed over these with the usual structure maps that are required to be C2 equivariant. And a genuine C2 equivariant spectrum has bigraded homotopy and cohomology groups. So here S A plus B alpha means the 1-point compactification of that representation with the C2 action coming from the action on the representation. And similarly, we have bigraded cohomology groups. And just one more quick definition, we say that a C2 equivariant spectrum is complete or co-free if the map from the spectrum to the mapping spectrum from EC2 plus into E, if that's a C2 equivalence. Okay, so that's a definition I'll need at some point in the talk. Okay, so those are just some definitions we need to get started. And so now the first sort of, from my point of view, the first really interesting example for us of a C2 equivariant spectrum is real cobordism. So this is just complex cobordism MU, but when we construct it, we keep track of the C2 action, which ultimately comes from complex conjugation. And so this can be constructed as a genuine C2 equivariant spectrum. And furthermore, all the usual things you do in non-equivariant chromatic homotopy theory, you can try to do here. So in particular, it turns out that there are classes VI that are classes in the equivariant homotopy groups of MU that live in degrees that are 2 to the I minus 1 times 1 plus alpha. So 1 plus alpha here is the regular representation of C2. So in multiples of the regular representation, I'll sometimes call these diagonal degrees. And so we have these classes VI, and if you forget the C2 action everywhere, so if you forget the C2 action on MU, you just get ordinary complex cobordism. If you forget the C2 action on 1 plus alpha, that just becomes a 2. Then you get the ordinary VIs of chromatic homotopy theory. Okay, so we have these equivariant lifts of the usual VIs, and so we can kill or invert them to produce a lot of the usual spectra we're interested in chromatic homotopy theory, but C2 equivariantly. So boldface En denotes equivariant Johnson-Wilson theory, whose underlying non-equivariant spectrum is the usual Johnson-Wilson theory. And then first defined by Pohu and Igor Kriz, if we take fixed points of this, this will denote the real Johnson-Wilson theories that I'll be talking about in this class.
Hi, Vitaly. This is Dan. Can I interrupt you for a second? Just for clarification. You know, when I look at the MU and you say the VIs, but there's all these other classes in MU also, right? As opposed to BP, right? So don't you have to do something with them also to get the ENs?
So those classes sort of come along. Like to actually construct VN, we just kill the VIs and invert them. So we still do have all those other classes there. So exactly, whoops. The homotopy groups of equivariant MU have all kinds of stuff in them. They're not as simple as the homotopy groups of ordinary MU. But if you just want to construct EN, then you can, do the usual stuff. The subtleties have to do with, if you want to argue that boldface EN, that equivariant EN is a, is a ring spectrum with some kind of structure, maybe homotopy, associative, or commutative, that kind of thing is difficult. And there are still some issues there. So sort of the best that Nitu and Steve and I were able to show is that it's a ring spectrum that's homotopy, associative, and commutative up to phantom maps, which is sort of good enough for studying the equivariant EN cohomology of spaces. But so that's where you kind of see difficulties because the homotopy groups of equivariant MU aren't so nice. Does that answer your question?
Yeah, thanks.
Okay, cool. Okay, so we've got the real Johnson-Wilson theories. So let me tell you a little bit about them. In particular, why I think they're interesting. So the first thing is that some of them are familiar. For n equals 1, the first real Johnson-Wilson theory is just real K-theory localized at 2. So if you've never seen the real Johnson-Wilson theories before, then I think you can get a good amount of mileage just by thinking about them by analogy to real K-theory. And ER2, after a certain completion, is TMF03. This was proved by Mike Hill and Leonard Meyer. So one big reason they're interesting is, unlike the Johnson-Wilson theories, and unlike any other complex-oriented theory, the real Johnson-Wilson theories have non-trivial Hurewicz image. So they pick up classes from the stable homotopy groups of spheres. So we already see that with ER1 in that KO detects eta. And in general, the Hurewicz image in ERN for all n, this was analyzed recently in a nice paper by by Guxuan Li, Danny Shi, Guozhen Wang, and Zhou Shu. So there's interesting stuff from the stable homotopy groups of spheres in them. And kind of going along that same direction, the real Johnson-Wilson theories are a first step away from complex-oriented theories. So if you like thinking about these things in the chromatic framework, then Kn locally, if you take ERN and Kn localize it, then Jeremy Hahn and Danny Shi recently showed that, this was a conjecture for a while, but they recently proved that we can get this as the homotopy fixed points of En here denotes Morava E theory, E lowercase e subscript n is Morava E theory, and you can produce them as the homotopy fixed points of Morava E theory, where this group H is sort of not so interesting. That just gets you to the Kn localization of En. And then it's this C2, which is central in the Morava stabilizer group, which is where you first start to get, this is what first makes the theory not complex oriented, and where you first start picking up things like torsion and a non-trivial Hurewicz image. So this is sort of the first interesting subgroup of the Morava stabilizer group in some sense. Okay, and I'll just mention this briefly. I won't really talk about this, but another reason to care about these is that the second real Johnson-Wilson theory, ER2, a connective cover of it is conjectured to be a split summand of string cobordism. And so, if we want to study string manifolds and their characteristic classes, then we might need to look in the ER2 cohomology of things. So this has been studied by a whole bunch of people. So that's another reason maybe to care about ER2. So those are all reasons why it's interesting. And then the other reason to study it is that we can very often compute it. And oftentimes we can compute it at all heights at once. So it's a very computable cohomology theory. And that's what this talk is really about. But despite being computable, this is where you first start to see some kind of interesting phenomena. And I want to talk about those by means of just an example. So let's look at the cohomology of RP9, just as a kind of random example. So if we look at the E2 cohomology, that's complex oriented. We know the E2 cohomology of RP9, and it's generated over the coefficients multiplicatively by this class U in degree 2. This is the first Chern class of the complexified real tautological line bundle over RP9. And this class has the property that if you take its fifth power, then it's in dimension 10. And once you pass the dimension of the space, you get 0. So the fifth power of this class is 0. Okay, that's E2 cohomology. Now let's look at the ER2 cohomology. So for now, let's ignore why I'm only looking at degrees that are multiples of 16, and let's also ignore the hat over here. I'll talk about why those are there later in the talk, but for now, at least in certain degrees, the ER2 cohomology of RP9 is generated over the coefficients multiplicatively by a class I'll call U hat. And this class is really related to the class U I mentioned above in E2 cohomology. Namely, if you take this class and you map from ER2 cohomology to E2 cohomology, then the image of this class is just the unit multiple of U. So it's some power of Vn times U, okay? And this class has the property that, so far we have the same analogy between E2 and ER2 cohomology, but the analogy breaks down in an interesting way in that the fifth power of this class, U hat, is no longer 0. In fact, the fifth power is 2 torsion, and it's the sixth power that's 0. So the case of RP9 was analyzed by Romy Banerjee, and this sort of speaks a lot to why the real Johnson-Wilson theories can be useful for certain applications. So again, an extra power, you just get one extra power of this generating class that survives beyond the dimension of the space. And this is something that doesn't happen in E2 or in general in complex-oriented cohomology theories.
Vitaly, this is Dan again. What dimension is U hat in again?
It's in degree -16, cohomological degree -16.
Okay.
Yeah, it's it's a certain power of V2 times U. Right, and so it's exactly this property, these extra couple of classes that you can try to use as obstructions. So Nitu-Kichlu and Romy Banerjee have used exactly these classes to prove some non-emersions of real projective spaces. And specifically, they build on Don Davis's approach to non-emersions using axial maps and BP2 cohomology. But the fact that they're working in a non-complex oriented theory that has these extra powers gives them a little more leverage. And so they're able to pull off kind of a few more non-emersions than Don Davis does with BP2 cohomology. And I'll talk a little bit more about, towards the end of the talk, if I have some time, about how we might try to get more non-emersions out of the real Johnson-Wilson theories. Okay, so now let me transition and tell you a little bit about computations. So what do we know about ERN? What do we know about ERN cohomology? So this was computed for spheres by Hu Kriz and then also by Nitu-Kichlu and Steve Wilson. So we know the coefficients of ERN. I won't talk about them so much, but you can look them up and they're not that bad. Sort of think about the coefficients of KO, and the coefficients of ERN are in some ways similar. So in particular, they have 2 torsion, and in fact, all the 2 torsion happens to be generated by a single class. So sort of a generalization of eta. Okay, so we know their coefficients. And we know ERN cohomology of projective spaces. So for RP infinity, this was computed by Nitu-Kichlu and Steve Wilson. And for CP infinity, this was computed in my thesis. And it's not sort of as obvious as you might think for CP infinity because ERN is not complex oriented. So you don't get the ERN cohomology of CP infinity for free in any way. You actually have to calculate it. Okay, and then if we look at it just for n equals 2, then for various real projective spaces, as I mentioned before, this was computed by Kichlu Wilson and Romy Banerjee, also for products of real projective spaces. Similarly, for n equals 2, in joint work with Nitu-Kichlu and Steve Wilson, we computed the ER2 cohomology of classifying spaces of cyclic groups and of finite dimensional complex projective spaces. And in fact, also in complex projective spaces, you see the same phenomenon where you get maybe 1 or 2 or 3 extra powers of a generating class, of a Chern class, surviving beyond where they would in a complex-oriented theory. Okay, also BUK, this is work that we're still writing up. And The big result I want to tell you about, which sort of computes the ERN cohomology for all n of a whole bunch of spaces at once, is the following. So this is the main result I want to talk about in this talk. So if Z is any of this following spaces, so if we take odd integral Eilenberg-MacLane spaces, or Z mod 2 to the Q Eilenberg-MacLane spaces if we just take the even ones, or for Z mod 2, we can take any of them. So very roughly, this is half of all Eilenberg-MacLane spaces. So if we take any of those, or if we take the following connective covers of BO, so BO, BSO, B spin, or the space I'll call B spin tilde, which is the fiber of P1 on B spin. So if you did the fiber of P1 over 2, you'd get B string, but this is just B spin. I'll say a little more about B string a little bit later. So for any of these spaces, there's sort of a uniform way to calculate their ERN cohomology. And you calculate their ERN cohomology by, so again, I'll say a little bit about the hat in a second, but roughly you calculate their EN cohomology, which you know, and then you base change the coefficients up to ERN. So here, this hat is something kind of weird. I'll explain later, but En hat is isomorphic to En, the coefficients of En. En hat star Z is isomorphic to just the En cohomology of Z. But the subtlety is that the isomorphism is as rings, but not graded rings. So there's a scaling of degrees happening. Okay, I'll talk about why that happens a little bit later. But just from a very practical point of view, if you're interested in computing ERN cohomology, then we know the En cohomology of these spaces, and all we do is base change, and we get the ERN cohomology. Okay, so that's the result I want to talk about. It's sort of a broad computation of the ERN cohomology of a whole bunch of things. Okay, so this is a computational homotopy theory seminar, so I want to get into the details of the proof a little bit. In particular, I want to talk about something called the projective property, which in some form is at the heart of a lot of computations about real Johnson-Wilson theory. And I think it's also something that could be more general than that. So I think this is something that it'd be really interesting if it could find a home in other contexts. I'll say more about that. So we want to compute the ERN cohomology of these spaces Z. And the way we're going to do that is we're going to start by computing the equivariant En cohomology of a related space I'll call Y. So this will be a space that has something called the projective property that I'll define. And it has the property that the space Z we're interested in maps to the C2 fixed points of Y. So really a good motivating example here is think Z equals BO. So we want to compute the ERN cohomology of BO. And BO is the C2 fixed points of BU. And BU will be an example of a space with this projective property. So our first step is we're going to compute the equivariant En cohomology of BU, where BU also has the C2 action by complex conjugation. Okay, so that's going to be the first step. And then the idea is once we have the equivariant En cohomology of these spaces Y with projective property, so like BU, then the idea is we just want to take fixed points in each component to get to the ERN cohomology of Z. So if I take the fixed points of equivariant En, then we get ERN. If I take the fixed points of Y, then I can map that over to Z. But of course, the subtlety here is the equivariant En cohomology of Y is bigraded. And we have this, it's ROC2 graded. So our group also acts on the spheres. It acts on the star coordinate over here. And so taking fixed points sort of isn't so easy because we also have an action on the spheres. And so these hats that you've been seeing, those are really essentially just a trick to take classes in the star degrees and move them over into integral degrees where we no longer have an action of C2 on the spheres and we can take fixed points to get into the ERN cohomology of Z. So that's the second part of the proof is sort of a trick to let us take fixed points of these things to land in the ERN cohomology of Z. And then the idea is we can write down some hypotheses on Y and Z that are satisfied by all of the spaces that I mentioned in the theorem, such that, so this will be the definition of what's called a Landweber flat real pair. And this will be enough to compute the ERN cohomology of Z as an algebra over the coefficients of ERN via a base change of the EN cohomology, which is known. Okay, so maybe this is a good spot to pause and ask if there are any questions about anything so far.
Hi, Vitaly. This is Prasid. Can you go back to the previous slide where you have the e-cohomology of KZN? Yeah, so what about what happens at the even dimension for KZ?
Oops, sorry. Backwards. Yeah, you're asking what happens if Z is an even dimensional plane space? Yeah, so the first example of this is CP infinity.
That's
CP
right.
infinity is a KZ2. So it's not so easy. You don't just get the ERN cohomology of CP infinity by a base change, but it's not that terrible either. Like essentially what you can do is, I won't talk about this too much, but there's a spectral sequence in the background here, the Boxstein spectral sequence, which goes from EN cohomology to ERN cohomology. And sort of, you have to calculate the D1 differential in this spectral sequence by hand. And then it turns out that after D1, then after that, it's not so bad. You can get sort of a similar base change type of thing, but after computing a D1 differential. So I think for things like CP infinity and maybe even conjecturally for some of the other, maybe for all even Eilenberg-MacLane spaces, conjecturally, I think you could still try to compute their ERN cohomology by calculating a Boxstein D1, which might require some work. And then after that, you might get the rest of the spectral sequence for free by sort of writing it as a tensor product.
Thanks.
Sure.
I've got a question also.
Yes.
Yeah, perfect, this formula. So this base change formula for ERN star of Z, I mean, I don't quite understand the hat thing yet, right? But it kind of suggests that all of the information in ERN star of Z is really in E hat N of Z to begin with. Is that?
Yeah, I think
the right idea.
Yeah, I think to a point. So I think the interesting thing that happens is, so this theorem works for RP infinity, for example. So we get the ERN cohomology of RP infinity from the EN cohomology of RP infinity. But the interesting thing is, once you throw in all of these coefficients, in particular the 2 torsion, the interesting thing is how these things interact with the classes in the EN cohomology. So these extra powers of a generating class that we saw before, these exactly have to do with the coefficients interacting with classes in the cohomology. So this theorem isn't true for finite dimensional real projective spaces. So sort of one thing you can do is compute the ERN cohomology of RP infinity and then truncate it and see how your results, how the coefficients interact with that generating class. So I guess this is something you can use to bootstrap to other spaces where this theorem isn't true.
Okay. All right, thanks.
Sure. Okay, so I want to spend some time now talking about this projective property. And this is the part that I think is more general than just real Johnson-Wilson theory. And I'd be curious how much of this could maybe find some analog in motivic homotopy theory over spec C, or maybe other contexts as well. Okay, so let me give you some definitions. These definitions really go back to some papers of Nitu Kichlu and Steve Wilson from, I think, like a decade ago. So we'll say a C2 equivariant space is projective if it's a wedge of smash products of CP infinities. Okay, so that's it, just a wedge of smash products of CP infinities, and there's a finiteness condition. Its integral homology is finite type. Okay, with this usual C2 action on CP infinity. Okay, so that's what it means for a space to be projective. And now we say a C2 equivariant H space Y is said to have the projective property if there exists a projective space X along with a point in C2 equivariant map from X to Y such that the mod 2 homology of Y is generated as an algebra by the image of this map. So a space has the projective property if there's an equivariant map such that the ordinary non-equivariant mod 2 homology of Y, its generators are given by products of classes that come from CP infinity. So in particular, an example to keep in mind is if you've seen hop rings before, then the mod 2 homology of the spaces in the omega spectrum for, say, MU or BP, or things like BU or BSU, these are all hop rings. And they're hop rings that are generated by circle products of classes from CP infinity. So that's why we allow smash products of CP infinities here. So they come just from circle products of classes that come from CP infinity, and that's the idea we're trying to get at here. Okay. Okay, so that's it. So a space with projective property it's just mod 2 homology is generated by classes as an algebra by classes that come from CP infinities. And these are all examples. So spaces in the omega spectra for MU or BP.
Vitaly, can I make a can I make a comment, a quick one?
Yeah.
I think the basic example would be that the homology of BU is generated by the image of BU1, that's CP infinity. So if you look at the integral homology of just the infinite Grassmannian, I mean, it's a standard fact that if you include CP infinity into BU as BU1, then all of BU is it's a polynomial algebra on that image. So that seems to be exactly the example that one should bear in mind in an example like this. That's your first example here, BU, but it's a straightforward one that everybody's aware of.
Yeah, thanks, Neetu. Yeah, that's a good point. Yeah, so for BU, then our space X would just be CP infinity. And then more generally, we need smash products of these things for the other spaces in the omega spectra for MU or BP. Okay, so this theorem, it's stated in our paper with in my paper with Neetu Kitchler and Steve Wilson, but really, the proof of this theorem and something very close to it shows up in older papers of Neetu Kitchler and Steve Wilson. So I think this is properly attributed to them. So let's let Y be a C2 equivariant H space with a projective property, as on the previous slide. So any of the examples we had before. And let's let E denote any complete MU module spectrum. So any co-free MU module spectrum will denote its underlying spectrum by just ordinary E, satisfying the property that the forgetful map, so the map that forgets the C2 action from the coefficients in diagonal degrees, coefficients in degrees that are multiples of the regular representation, to the ordinary E cohomology in even degrees, we want this map to be an isomorphism. So I'll give some examples in a minute, but MU itself will be an example of such a thing. So will the equivariant Johnson-Wilson theories. Okay, then the theorem says that in fact, the forgetful map on the equivariant cohomology of Y is an isomorphism as well. So we get the equivariant cohomology of Y from the ordinary cohomology of Y in even degrees. So that map is an isomorphism. And in fact, the theorem, this is the part of it that I'm going to use for the computation that I told you about. But in fact, the theorem says something stronger. It says that the E cohomology of Y is a free MU star module on generators in even degrees. And the equivariant E cohomology of Y, ROC2 graded equivariant cohomology of Y, is a free module over the coefficients of MU on the equivariant lifts of these generators that come from the cohomology of ordinary non-equivariant cohomology of E. So the point here is this constitutes a computation of the full equivariant cohomology of Y as a module over the coefficients. Any questions about that? Okay, then I'll keep going. Right, so that's the result. So we compute the equivariant ecohomology of Y. And examples here include the equivariant Johnson-Wilson theories, or MU, or BP. For BPN, the spectrum is not complete, so we need to complete it. So if you take the mapping spectrum, then it'll be true for that as well. And then, like I said before, examples of spaces with the projective property include all of these. So in particular, this constitutes a computation of, say, the equivariant MU cohomology of the diagonal spaces in the omega spectrum for MU. So these are equivariant unstable MU operations. So this gives us access to things like that. Okay, so I want to spend some time talking about the proof of this theorem. One reason is that I'm interested in whether some part of this proof could be adapted to other situations. So this is more general than just being about Johnson-Wilson theories. In general, it's about several C2 equivariant spectra. So we want to compute the ROC2 graded cohomology of Y. And the idea is we're given a projective space X, so a wedge of smash products of CP infinities. And we have a C2 equivariant map from X to Y, which generates the mod 2 homology of Y. So from that, right away, we get that the mod 2 homology of Y is even, since the mod 2 homology of wedges of CP infinities is even. And we get the integral homology of Y is free and even. OK, now let's take the James construction. So Y is a C2 equivariant H space. And so our map from X to Y lifts to a map from the James construction on X to Y, a C2 equivariant map that lifts this F. And now let's run the Atiyah-Herzberg spectral sequence. And let's just do it non-equivariantly for now. So this comes from filtering the CP infinities skeletally. And the Atiyah-Herzberg spectral sequence collapses. Everything here is in even degrees. So it collapses for both MU and for Y, and they're both free since the homology is free. So they're both free, and this map in MU homology from the MU homology of the James construction to the MU homology of Y is a split surjection. And what we're going to do is we're going to choose a basis for the subspace of the MU homology of JX on which this map is an isomorphism. Okay? So we choose a subspace of the MU homology of JX, which is isomorphic to the MU homology of Y. So this is all stuff that we get just from having a projective space X mapping to Y, whose image generates its mod 2 homology. Okay. Now let's try to do the same thing equivariantly. So we can get the Atiyah-Herzberg spectral sequence from a skeletal filtration of our space. So let's take the usual skeletal filtration of CP infinity, but remember the C2 action. And now the associated gradient of that is going to have spheres in diagonal degrees, in multiples of the regular representation. And we run the Atiyah-Herzberg spectral sequence equivariantly. And from that, we can conclude that the equivariant MU homology of JX, so the idea here is we know the equivariant MU homology of CP infinity from the real orientation of CP infinity, and the Atiyah-Herzberg spectral sequence for MU homology of JX. JX is just a wedge of smash product of CP infinities. It behaves the same way. And so we get that the MU homology of JX is free over the coefficients of MU on generators in these diagonal degrees. And we're going to do the same trick. We're going to take our basis that we found before non-equivariantly for a subspace of the non-equivariant MU homology of JX, and we're going to lift it to an equivariant basis for some subspace of the equivariant MU homology of JX. And let's take, so here when we lift this, we're really secretly using the fact that, never mind, I use this later, never mind. So, okay, we lift this basis, and let's define the free MU module spectrum on this basis. So it's just the wedge of, we take only the summands that correspond to the elements in this basis. Okay, so we take the free MU module spectrum on this basis, and we include it into the MU homology of JX. So we take this and we include it into the full wedge, and then we map over to Y smash MU. And from the way that we constructed things, if we forget the C2 action everywhere, then we constructed this so that if I forget the C2 action on this basis and on everything, then this map is a non-equivariant equivalence. Because this basis beta beta bar, it lifts beta, and beta was chosen so that non-equivariantly this is an equivalence. So this is an equivariant map, which is a non-equivariant equivalence. So we can smash it with EC2 to get an equivariant equivalence. And now the trick we're going to do is we're going to map out of this equivalence in the category of MU module spectra. We're going to map out of this equivalence into E, into our complete MU module spectrum E. And then we'll adjoin the EC2 plus over and use the completeness of E. And that gives you an equivariant equivalence between the mapping spectrum from this space with projective property into E to a free module spectrum over E. So we get a computation of the ROC2 graded cohomology of Y, E cohomology of Y. Sorry, this E here should be boldface. That's a typo. This should be boldface, so should this one. We get that as a free module over the coefficients. Okay? So this is how we compute the equivariant cohomology of spaces with projective property Y. And I'd be interested to hear after the talk. I don't really know anything about motivic homotopy theory, but I think a lot of you do. So I'd be interested in knowing how far we could get trying to run this argument motivically for over spec C for something like MGL and sort of an analogous definition of spaces with projective property. I wonder if we could produce this map motivically and maybe have it be an underlying have it Betty realized to a topological equivalence. And then I wonder if some version of this last part of boosting it up to an equivariant equivalence, if some other kind of argument maybe could get you to a motivic equivalence. This is relevant to this motivic Wilson space hypothesis that Mike Hopkins has spoken about. So the idea is if the spaces in the omega spectrum for MGL sort of are Wilson spaces, as Mike Hopkins defines them, then this would be true. So it'd be interesting to see how far this argument gets you. Okay, so maybe we can talk a little bit about that after the talk if people have thoughts. I'd be interested in hearing them. Okay, so now I want to talk about the second part of the proof, specifically how we get from the equivariant E cohomology of Y to the ERN cohomology of Z. So the key idea here is Mitu Kitchler and Steve Wilson observed in the coefficients of the equivariant cohomology of E, they observed this invertible class called Yn. So it lives in, so there's this messy looking thing lambda, but the point is lambda is an integer, and it lives in degree an integer plus just a single copy of the sign representation. And this class is invertible. And in fact, its underlying class is underlying non-equivariant class is a power of Vn. And so what we can do with this class is we can multiply by its powers to shift any class we have in the equivariant En cohomology of any space into integral degrees. So pretty much we just take any class, we look at the number of sign representations there are, and we multiply by the corresponding power of Y to get rid of all the sign representations and put it into integral degrees. So I'm going to use this construction specifically for classes that live in diagonal degrees, even though you can do it more generally for classes in any ROC2 graded degree. So given a class in degree k times 1 plus alpha, k times the regular representation, there are k copies of the sign representation. So I'm switching from homotopy degree to cohomological degree. So I need to multiply by the kth power of Y to subtract off k copies of alpha to put it into an integral degree. And it turns out to be in degree k times 1 minus lambda. When n equals 2, lambda is 17, and this 1 minus lambda is negative 16. So this is relevant to why I had degrees that were multiples of 16 earlier in the talk. Okay, so those are sort of the nice degrees that come from the classes in diagonal degrees. Okay, so we can multiply by a power of this class to get rid of all the sign representations and put us in diagonal degrees. And if you forget the C2 action everywhere, then all you're doing non-equivariantly is you're taking a class in the En cohomology of Y in even degrees and multiplying by some corresponding power of Vn. And this fits into a diagram where So this hat construction, what it does is for every class in the equivariant cohomology of y, it multiplies it by the appropriate power of this invertible class yn and shifts it into integral degrees. And then down here, we have just the non-equivariant shadow of what's happening. So that's all this hat construction is it's a trick for moving classes in ROC2 grading into integral degrees. And of course, which power of yn you multiply by depends on what degree you started in. Okay. So that's why there's this scaling of degrees that's happening. Okay, so we have this hat construction. And now let's use that in combination with what we had before. So we have a space Y with the projective property, so think BU. And we have an isomorphism now we proved that we have an isomorphism from the equivariant EN cohomology of BU, in particular in these diagonal degrees, to the ordinary cohomology of BU, or in general Y, in even degrees. So think, what kinds of things generate the EN cohomology of Y, of BU? It's Chern classes, and we have equivariant lifts of these Chern classes living in the equivariant EN cohomology of BU in diagonal degrees. So let's work backwards. This map is an isomorphism, so let's go backwards. Let's take the EN cohomology of Y in even degrees. So this is something we know in all of the examples that I said. And we take row inverse, we take this isomorphism backwards to end up in the equivariant cohomology in diagonal degrees. And then we apply the hat construction to it. So we shift all these classes into integral degrees. Yes, the asterisk is the same, but yeah, sorry, for those listening, Doug asked if the asterisks are the same, and yeah, this is just an ordinary integer asterisk. So you get classes in even degrees. So there's a rescaling of degrees that happens here. Classes in even degrees end up in classes that are multiples of 1 minus lambda. So something in degree 2 goes to something in degree -16 if n equals 2. And something in degree 4 goes to degree -32 and so on. Okay, so let's call this composite psi sub y. So this takes classes in the even cohomology of y and produces classes in the integral graded equivariant cohomology of y. And the idea is where these classes end up, we're now in a good place to take fixed points because there's no longer a C2 action on the spheres. So suppose we have our space Z, which has no C2 action, and a map from Z to the C2 fixed points of Y. So this is BO mapping in as the C2 fixed points of BU. And we can make this composite. So we take the psi Y that we defined up here. So we take classes in the even EN cohomology of Y, produce classes in the equivariant integral cohomology of Y. And then all we do is take fixed points on both components. So we get a class in the ERN cohomology of the C2 fixed points of Y, and then we map that over to Z. So we get classes in the ERN cohomology of Z in these weird scaled degrees. And let's call this composite chi sub Z. So this is a way of taking classes in the even EN cohomology of Y, which we know, and producing classes in the ERN cohomology of Z. Okay, so now I'm ready to define a Landweber flat real pair. So these will be the spaces for which that theorem I stated at the beginning, that computation applies. So assuming everything as before, so we have a space with projective property and our space Z maps into the fixed points of that space. Let's assume further that this composite from Z to Y, so from BO to BU, induces a surjection in EN cohomology. So this isn't just an ordinary non-equivariant EN cohomology. We have a surjection from the EN cohomology of BU to the EN cohomology of BO. And furthermore, let's assume that this triangle has a factorization. So I can go from the even EN cohomology of Y to the ERN cohomology of Z, or I can map to the EN cohomology of Z, and let's assume there's a factorization in this diagram. So this is sort of a technical condition, and it turns out that producing this factorization often comes down to finding short exact sequences of hop algebras in KN cohomology that were produced in sort of lots of interesting papers of, for example, Ravenel-Wilson and Ravenel-Wilson and Yagida and Kitchlew, Wilson, and Laura's. So this is a factorization that you can get from previous work. We don't generally have to work too hard to produce this. So I won't get into this part of the proof in too much detail, but let's assume we have these two conditions, and let's assume furthermore that the BP cohomology of Z is Landweber flat. Then we call this pair of Z and Y a Landweber flat real pair, and the theorem is that if we have a Landweber flat real pair, then we can compute the ERN cohomology of Z as a base change of the EN cohomology of Z up to the coefficients of ERN. So here I can tell you what this notation is now. En hat star Z is just the image of this map chi sub Z. So this composite we formed here, we call its image En hat Z. And what it is it's a copy of the En cohomology of Z inside the ERN cohomology of Z, but with a scaling of degrees. And so we get an isomorphism. So we take this algebra inside the ERN cohomology of Z. It's something we know. It's isomorphic to the EN cohomology of Z, and we just base change up our coefficients, and we get the ERN cohomology of Z. And here are the examples that we apply this for. So here, the space Y is sort of an auxiliary space that we need to compute the ERN cohomology of Z. At the end of the day, this is a statement about the ERN cohomology of Z and not the ERN cohomology of Y. So for the Eilenberg-MacLane spaces, we end up using spaces in the omega spectra for truncated BP, and then these are the spaces for connective covers of BO. And in particular, we also get a result for B string, but it turns out to only hold for n less than or equal to 2. All of the other results here are for all n, but for B string, it's just for n less than or equal to 2. Okay, are there any questions? So this last part of the proof is a little bit technical, and I didn't really get into the details of this definition of a Landweber flat real pair, but really the intuition is calculate the equivariant cohomology of Y and then take fixed points and put conditions on Y and Z so that this actually works. So any questions about this? I just have a little more I want to say, but this is a good place to pause. Okay, cool.
Okay.
So
Vitaly, if you could just take just a couple more minutes and so we can wrap up a little bit before 12:30.
Yeah, sounds good. I have like 2 more minutes, yeah. So just a few words about a potential application that I think it would be really good to apply this to. So this is work in progress with Nitu Kitchlew and Steve Wilson. So one thing is it'd be interesting to compute the ERN cohomology of the spaces in the spectrum for ERN. In other words, we've taken fixed points on both components. So these would correspond to unstable ERN operations, even for just specific values of K that are multiples of this 1 minus lambda. This would be an interesting thing to have. I guess probably cohomology. Yeah. Doug asked if I mean homology and cohomology, and yeah, I think that's a typo. I really mean cohomology. Yeah, we want to act on we really know the ERN cohomology of spaces, so we want cohomology here. So it'd be nice to apply this to prove some immersion or maybe non-immersion results. So one approach to this problem is as follows. So if I have a real projective space and it immerses in some Euclidean space, then this happens if and only if n plus k plus 1 times, so 1 plus the dimension of the Euclidean space, if I take that multiple of the tautological line bundle, if that has n plus 1 linearly independent sections. Okay, so now I want to combine that with a result of Nitu Kitchlew and Steve Wilson that 2 to the n plus 1 times any vector bundle is ERN orientable. So for example, 4 times any vector bundle is KO orientable, 8 times any vector bundle is ER2 orientable. This is not optimal even for KO, but this is a result that they got. And so if 2 to the n plus 1 divides n plus k plus 1, then we know that n plus k plus 1 times this bundle has an ERN Tom class. And the idea is if the bundle has n plus 1 linearly independent sections, then then the bundle splits off an n plus 1 dimensional trivial bundle. So the Tom space is an n plus 1 fold suspension. And so you might hope that if you take unstable ERN or equivariant EN operations and act on this, you might be able to detect whether or not the space is a suspension. Yeah, is there a question? Okay, yeah. So the point is, very roughly, acting by unstable operations on a Tom class might give us a way to detect suspensions. And this is work in progress. And maybe I'll stop here.
Hello, Vitaly?
Yes.
Can you hear me?
Yep.
The n in the theorem is different from the n of RPN. Am I right?
Oh, shoot. Yes, absolutely. Yeah, sorry, that's a typo. The n of RPN and of Rn plus k is not the same as the n in ERN. Yeah, my bad. That's a typo. One of those should be an m.
In other words, you're just thinking of immersing RPM, as in Mary, into some R of m plus k, and you're trying to address that question using ERN, as in Nancy, correct?
Yeah, absolutely, yeah. Yeah, the dimension of the projective space doesn't have to be the n in ERN. Yeah, thanks for pointing that out.
Okay, I'm going to unmute everyone so we can thank Vitaly. Go ahead and thank him. Okay, and I'm going to now mute everyone again just to cut down on background noise. Okay, and I'm going to unmute you, Vitaly. Okay, further questions?
Can I make a comment, if it's okay?
Sure.
I think you mentioned at some point in your main theorem, it's a theorem about the cohomology, the ERN cohomology of Z, and Y is an auxiliary space.
Yeah.
Right? So Y doesn't play into the statement of the theorem, but I think it's a little subtle, right? One should point out that the way this E hat Z sits inside ERN Z actually depends on Y. So Y chooses the forms of the EN cohomology of Z that sit inside ERN. So Y is somehow, it's dictating how this hatted object sits inside the ERN cohomology of Z. So it's playing a subtle role.
Yeah, that's a good observation. Yeah, so yeah, sort of choosing a Y is something like choosing multiplicative generators for the ERN cohomology of Z. Depending which Y we choose, exactly that. Different Ys might give us different subalgebras here, as subalgebras of ERN Z.
Other comments or questions? Okay, I'm going to go ahead and unmute everyone again. Let's thank him one more time. And next meeting, 2 weeks, Dan Duggar is speaking. We'll see y'all then. We'll be hanging out here for a little while afterwards. You're welcome to stick around and chat. Thanks, everyone. All right. Well, thanks very much, Vitaly. Was a little bit tricky trying to juggle the live audience and the electronic audience also, or maybe it just didn't really matter very much.
So yeah, I'm kind of curious if anyone who knows something about motivic homotopy theory knows how much this kind of computation might work for MGL and like the spaces in the omega spectrum. Yeah.
So I have no idea about the spaces in the omega spectrum. I'm just the wrong person to ask about that. But you know, this sort of focusing on the star 1 plus alpha degrees is something that most definitely like happens motivically. So anyway, there's all kinds of tools you don't have, like taking fixed points and so forth. You don't have fixed point functors and so forth. So I'm not saying that not everything works the same. But yeah, I don't know.
So can I ask a very basic question for motivic homology?
Sure.
So if I have a map between two motivic spectra, that is an equivalence if you just go back down to equivariant spectra.
Yeah.
Actually, go down to equivariant spectra and then just forget the fact that they are equivariant spectra. So just go to the naive world of spectra.
Yeah.
From motivic to equivariant and then forget down to regular spectra. That original map is an equivalent. Is there something like EZ2 that frees it up originally to make it an equivariant motivic equivalence? Like, is there something like the EC2, which Vitaly has on the screen right now, that takes an equivariant map, which is an underlying equivalence, and makes it into an equivariant equivalence?
I don't think so. But I guess I don't know for sure. I would not expect such a thing to be true. I think that's kind of getting right at the difference between the R motivic and the C2 equivariant behavior is precisely the kind of like the fact that this sort of EC2, the C2 plus is kind of missing for EC2 plus. But yeah.
I was talking to Nicola about this, and he was saying like maybe some of this co-fiber of tau stuff might be relevant. Like if you show both, because like going to an ordinary topological, into that category is like setting tau equal to 1, and then
right,
we're able to show that it's also like if you mod out by tau and show that you get an equivalence of co-fiber of tau modules, would that together imply a motivic equivalence?
Well, probably. I have to think a little bit more about that, but that's the sort of thing that philosophically that's the right idea anyway.
Mm-hmm.
All right, that was a great talk.
Yeah, thanks very much, Vitaly. This ERN stuff is just a topic that just kind of keeps giving, doesn't it?
Yeah, so far, yeah.
Nice.
Yeah. All right, excellent.
Thank you. See ya.